Hello, so today we'll be discussing damped harmonic motion. So damped harmonic motion is the motion that occurs when the amplitude of any real oscillating motion decreases through time until it comes to a stop. So for example, we have this object that's attached to a spring and it will oscillate back and forth until it eventually comes to a stop. Now, this is because instead of potential energy and kinetic energy being transferred to one another, they are both transformed into thermal energy instead. In damped harmonic motion, there are two types of forces. So first of all, we have the damping force, and this force acts on the object and hamper its oscillation, which consequently creates the damped harmonic motion. So the formula states that the damping force is equals to the negative of the proportionality constant multiplied by the velocity of the oscillation. The second force is the restoring force. So recall that Newton's second law of motion states that the net force of an object is equal to its mass multiplied by its instantaneous acceleration. The restoring force is created by the spring in the system, which is given by Hooke's law that states the negative of k multiplied by x. So now we have the negative of k times x minus b times v equals to ma, and if we move ma to the right, we will have an equation that looks something like this, and in damped harmonic motion, we will need an equation that only includes the displacement values. So then the instantaneous acceleration needs to be replaced with the second derivative of our position function with respect to time, and we will also need to be replaced with the first derivative of our position function with respect to time. The equation will look something like this, and it's called the equation of motion. Suppose our solution for this equation falls under the general solution, which is displacement x to time equals to the amplitude times e to the power of negative gamma times t times cosine of omega prime times t. Assuming that at time equals 0, our displacement is the highest or the amplitude, so the value of the 5 terms we have in our equation will go to 0. Now this solution would work under two conditions only. First being omega prime needs to be equal to the square root of k divided by m minus b squared divided by gamma times m squared. And the second condition is that the gamma needs to be equal to b divided by 2 times m. Thus, substituting this value into that equation will give you the equation for a slightly oscillating object. Next, we have the frequency of damped harmonic motion, which we can start by using the formula frequency prime equals to omega prime divided by 2 pi, which then we can substitute omega with this value, and we will get the equation that will be used for our calculation. Essentially, the equation tells us that the frequency of damped harmonic motion is lesser than the frequency of simple harmonic motion. This equation really comes in handy for determining which type of damping is an object experiencing. Suppose we're taking this term and derive it to b squared equals to 4mk. If both value of masses are equal, the entire terms becomes 0, suggesting that the object will eventually reach equilibrium. Now this brings us to our final topic, which is the three types of damping. First is overdamped, in which b squared is much larger than 4 times m times k, and this is when an object takes a very long time to come to a stop. Next is underdamped, in which b squared is lesser than 4 times m times k, so an object will oscillate a couple times before it stops completely. Lastly, we have critical damping, in which b squared is equals to 4 times m times k, meaning the object takes the least time to come to a stop.